Alright, hi everyone. This is our online lecture for June 27th, and we're going to be going over 19.1, which is the equilibria of acid and base buffers. So here are the learning objectives. We especially want to pay attention to the first one for this section, and we're also going to have a few calculations in there as well. Okay, so the whole idea of this section is acid-base buffers. So we've already talked about equilibrium, we've talked about acids, we've talked about bases, and now we're going to talk about buffers. So basically, if we have a solution and we add some, say, nitric acid, strong acid, the solution we know is going to turn acidic. But what we can do is have a buffer, and when we add the nitric acid, it actually won't change the pH very much. So there's only a minor change in the pH. That's what I just said. Okay. So a buffer has to have an acidic component and a basic component, because what we need is kind of this conjugate, this acid and conjugate base, or base and conjugate acid. And when we add a strong base or add a strong acid, it needs to compensate. But we can't just have any acid or base because they would neutralize each other. So that's why we have to have that conjugate acid-base pair. So a lot of this chapter actually really goes back to chapter 18. So I know you're studying right now and you're kind of stressing out about this, but a lot of what I'm talking about today will actually kind of help you review a little bit. So for this buffer where we have to have a conjugate acid-base pair, we have to have a weak acid and its conjugate base, or a weak base and its conjugate acid. So an example of this is, say we have diluted HCl, pH 5. We add some more HCl, it goes right down to pH 2. And if we add NaOH, it goes up to pH 12. But if instead we have an acetate buffer where we mix acetic acid and sodium acetate, we basically provide this environment, this buffer, where if we add more strong acid right here, it only goes down by 0.02 pH units. And if we add NaOH, it only goes up by 0.02. So this is really important, especially in my research, where we're making mobile phase buffers, where we need to maintain a consistent pH throughout our whole experiment, our whole run. So we use buffers quite a bit so that if something happens with the, say your sample is slightly acidic and you introduce it into the environment, it won't dramatically change the pH of the whole system. So our first question for the quiz, what is the purpose of a buffer? So I really want you to try to not copy the definition. I know that's kind of ingrained into our head to do that, but really try to explain it in your own words. Okay, so we're going to go into buffers and the common ion effect. So we have that example of an acetate buffer. So we actually have the acetate ion on both sides of the reaction. So this is called the common ion effect. So if we have acetic acid and water and the acetate ion, basically if we add sodium acetate, that's going to provide more of the acetate ion, which we know is going to shift the equilibrium to the left. And if we add that ion, basically shifting it to the left will cause less of the acetic acid to dissociate. So here's just a chart showing if we just have the weak acid, and then when we have the weak acid with a conjugate base, so these three would be the considered buffer solutions. And you can see the percent dissociation here and the pH. So without any acetate ion, we have a pretty low pH, but when we even add just a little bit of acetate ion, we actually maintain a pretty steady pH here. So we can calculate percent dissociation like we did before. So this is just the concentration of the acid dissociated over the concentration of the initial. times 100. Okay, so we know that the buffer has to have two components, HA and A minus, and when we add a strong acid or a strong base, it has to be able to consume that and kind of shift the equilibrium to compensate, to kind of cushion that pH. So on the left here, if we add, say, NaOH, a strong base, it's going to react with the weak acid, and it's going to cause a shift to the right. So we're going to use up some of that acid here, and it's actually going to produce more of the CH3COO minus. Then if we, on this side, if we add more H3O plus, it's going to react with the ion and cause a shift to the left. So basically, because it shifts and compensates, we don't have a large change in pH. So here's more of a visual representation. So here, if we have equal concentrations of HA and A minus, if we add some strong acid or if we add some strong base, the buffer compensates for it. Okay, so to get a little bit more into the nitty-gritty, we know that we can find the Ka for this reaction. So this is, something you're going to have to know for the exam. But if we kind of manipulate this, what we can do is say the concentration of H3O plus is equal to the Ka times this ratio of the acid concentration over the base concentration. If we go a little bit further, we know that Ka is constant. Ka remains the same if it's the same reaction at the same temperature. So that means that we can make a direct connection between H3O plus and this ratio. So if the ratio increases, that means H3O plus increases. And if the ratio decreases, H3O plus decreases. So we know that the buffer components consume nearly all of the added acid or base to compensate. So as long as that amount of acid or base is pretty small compared to the amount of the buffer in the solution, then there will be a very small change in the pH because it has a small change in that ratio. So here's your second question. A buffer solution containing 0.2 molar HA and 0.15 molar A minus has a pH of 3.35. So if 0.0015 moles of NaOH was added to 0.5 liters of buffer, what is the new pH? So we're going to assume the volume change is negligible. So I'll walk you through a little bit of this to help you out. So here, this is our IACE chart. It's a little bit different. So we have our initial, and we're given the pH, so that means we know how to calculate H3O+. So that'll be another thing you have to know for Wednesday. And then A is the added. So here we're adding the NaOH. So all of the NaOH will react with all of the HA, and it's going to produce some A minus. So from that, we can calculate this box and this box. Then we can figure out what the equilibrium concentrations are and add in the changes here and all of that. And we know that Ka is constant, so then we can use that to help solve the problem. Okay, so I just made you do that really long problem, but actually there's a Henderson-Hasselbalch equation where you can actually sort of take a shortcut, and we know that we already have this ratio here. So what we can do is if we take minus the log of each of those components, we get something that looks very similar. We know this as pH. We know this as pKa. So we can get an equation where the pH equals the pKa plus the log of base over acid. So you might wonder why we have acid over base here and base over acid, and it's simply the math and the conversion. Okay, so after doing that long problem question 2, for question 3, I'd like you to show how you could have used the Henderson-Hasselbalch equation to answer that question. So hopefully you'll get the same answer for both of them. So buffer capacity is kind of how strong is the buffer? How is it able to, how well is it able to kind of cushion that pH change? So if we have more of the buffer components, that means it has a greater capacity to resist the pH change. The other thing is, if the component concentrations are close to each other, so if that ratio is closer to 1, it has a greater buffer capacity. Because the concentration ratio, remember, determines the pH. So if the ratio doesn't change very much, the pH won't change very much. It's also important to know that the buffer pH is independent of buffer capacity. So you could have a buffer that's at 6 and a buffer at 8, and maybe one is stronger than the other, but maybe you have a buffer at 6.1 and that one is actually not as good as this other buffer system at 6. So they're totally not related. So we also have buffer range. So buffers only work within a certain range of pH, because if we add too much acid or too much base, it's going to change. But also, if we have a different ratio for those buffer components, it's not going to be very effective. So if we have one component that's more than 10 times the other, it's going to be a really bad buffer. So usually buffers have a range of plus or minus 1 pH unit of the pKa of the acid component. So question 4, in your own words, define buffer capacity. And it might help to kind of give an example or something. And what factors influence the buffer capacity? And in question 5, what do you need to achieve the greatest buffer capacity? Okay, so there's different ways to prepare a buffer, but the first thing we have to do, we know it needs to have a conjugate acid-base pair. So we need to try to choose the best pair. So the way that we do that is, say we want to keep a solution at pH 6. We need to find a pKa of the weak acid component that is close to 6. Then we can calculate the ratio of the buffer component concentrations that we need to give that pH. And then we can calculate how much volume we need and how much we need for each of the components, the mass. And then mix them all and correct the pH. So there's another way we can prepare a buffer, and we can do this from one of the components by partial neutralization of the other. So here we can actually prepare HCOOH and an HCOO minus buffer by taking aqueous HCOOH and NaOH. So by doing that, say we didn't have any HCOO minus solution around, what we can do is kind of take that HCOOH acid, and by mixing it with a little bit of NaOH, we're going to produce some of the ion and water, and we'll still have some of the HCOOH left over. So here's another question. Which of these pairs of substances cannot be mixed together to give a buffer solution? And I'd like you to just write a little bit about why. Okay, I have to do some sort of practical application, of course. So here, a lot of shampoos have the label pH balanced. So I want you to think about why they would make a pH balanced shampoo. So you want to think about the pH of soaps and detergents and the effect of such a pH on, say, sensitive skin on your scalp. Okay, so I'd like you to do a quick summary here. And when you're done with that, I'd like you to do the final question if you have any feedback for me. So I know that was kind of quick, but you can watch it a few times. And I hope you guys have a great weekend, and I will see you on Monday. So if you have any questions, about the exam or whatever, you can try to email me. I'll have limited access. But see you on Monday.